Welcome to my video course on mastering ERTMS ETCS signaling systems. I am absolutely thrilled to have you here today. We're going to take a journey deep into the core mechanics that keep global rail networks moving safely and efficiently. Whether you're a seasoned rail operator or just, intensely curious about the technology that prevents high-speed disasters, this explainer is going to break down exactly how modern systems pull off the seemingly impossible. Let's get right into it.
Here is our roadmap for today. We'll be looking at the evolution of signaling, track circuits and detection, automatic train protection, interlocking fundamentals, and we'll wrap up with infrastructure capacity.
Section 1. Evolution of Railway Signaling.
All right, before we get into the digital wizardry, we really have to grasp the golden rule of railway safety. It's governed the industry since the 19th century. Trains simply cannot collide if they aren't permitted in the same section of track at the exact same time. Right? Looking at this timeline, you can see how our methods for enforcing that rule have shifted over the years. Back in 1850, we literally had men standing along the tracks with stopwatches using hand signals. Imagine the margin for error there. By 1900, we brought in mechanical semaphores. The 1930s revolutionized things with electrical track circuits and optical signals, finally removing the need for manual human intervention. By the 80s, we saw the introduction of automatic train protection, or ATP. And finally, we arrive at the modern era with ERTMS, the European Railway Traffic Management System.
It's honestly a massive technological leap. We go from a guy in a top hat hoping the line ahead is clear for a steam locomotive, all the way to a sleek, modern train constantly communicating with radio networks under one interoperable ERTMS standard. It is a total shift from human reliance to absolute digital precision. But to really understand the digital stuff, we first need to understand the physical.
Section 2. Track circuits and axle counters.
So how does the railway actually physically know that a 400-ton piece of metal is sitting on a specific block of track? Well, it comes down to the sheer elegance of the 1872 DC track circuit design. You are looking at a block of track isolated by insulated joints. At one end, you've got a battery. At the other end, a relay. When the block is clear, meaning no train is anywhere in sight, the electrical current just flows from the battery right through the rails and energizes that relay. And when that relay is picked up, your signal glows green. It is actively confirming that the path is clear.
But watch what happens when a train actually rolls in. The train's steel wheels and axles literally bridge those two rails together. This physically shorts the battery circuit. Instantly, the current flowing to the relay drops to zero. The relay drops, the green light cuts out, and boom, the red light comes on. It's brilliant because it's a physical absolute. If a wire snaps or if the battery just dies, the relay loses power and the signal defaults straight to red. A dark or red signal always means stop. You only get a green light when the circuit actively proves it's safe. Now, track circuits aren't the only game in town. Enter the axle counter. Instead of a continuous electrical circuit, this uses a really clever check-in, check-out logic. Magnetic sensors at the start of a block physically count the train axles rolling in. Then, sensors at the far end count the axles rolling out. Only when that net count reaches exactly zero does the system definitively know the train is left, and it clears the block for the next one. It is an incredibly precise alternative.
Section 3. Automatic Train Protection and ERTMS.
Okay, so we know where the train is, but how do we actively control it? This is where we move from passive detection to active, automated supervision. The absolute heart of modern rail safety is the safe braking protection curve. Older systems just flashed a red light and, hoped the driver stopped. But ATP systems mathematically model a protection curve, instant by instant. The system continuously calculates the maximum safe speed based on exactly how far away a stop signal is. If a driver ignores a warning and the train's actual speed pierces that curve, the system doesn't ask for permission. It automatically intervenes and slams on the brakes. It literally mathematically enforces safety.
Within the European Train Control System, or ETCS, we see two major operational paradigms. ETCS Level 2 still relies on those fixed track blocks we just talked about, paired with continuous GSMR radio communication and physical track beacons called Eurobalises to calibrate position. But ETCS Level 3? That represents the absolute cutting edge. It tosses out fixed physical blocks entirely in favor of moving blocks. It relies on absolute braking distances, calculated continuously around the train itself, which totally removes the need for fixed physical track release devices. And since these trains are flying across entire countries, they rely on radio block centers, or RBCs. Imagine a train hurtling along at high speed. It's going to quickly leave one RBC's jurisdiction and enter another's. This requires a perfectly seamless handover process. The handing over RBC tracks the train right to the border. talks to the accepting RBC, and passes along the exact train profile via the GSMR network. The driver doesn't even lift a finger. The whole data transition happens flawlessly in the background.
Section 4. Interlocking Fundamentals.
It's one thing to run a train in a straight line, but what happens when they reach a complex, sprawling station? This is where our interlocking fundamentals come into play. Imagine we've got a train at point A needing to navigate to point B, and there are multiple diverging paths it could take. When the system initiates route setting for a specific path, it immediately performs point locking. This physically secures the switches in the correct alignment, so there is zero chance they can move under the train. At the exact same time, the system provides flank protection. This means it proactively sets adjacent switches to divert any other trains that might accidentally slide into our protected path.
The absolute foundation of this entire operation is route locking. Once that route is set, every single switch and block section involved is locked down as a mutually exclusive shared resource. Through continuous conflict detection, the system ensures that absolutely no overlapping routes can ever be set up. Until our train fully clears the path, the interlocking system will stubbornly refuse to let any other train access even a fraction of that shared resource. It acts as an invisible, impenetrable shield, protecting trains at every single junction.
Section 5. Increasing infrastructure capacity.
So you might be wondering, why invest billions into these incredibly complex digital signaling and interlocking networks? Well, it comes down to one magic word: capacity. What you should really take away from this explainer is that upgrading to ERTMS is the smartest economic choice a railway can make. By continuously monitoring trains and automatically enforcing those braking curves, we can safely reduce the headways, the actual physical distance between trains. We can run them faster and much closer together, without compromising safety one bit, completely removing the risk of a driver running a red light. Essentially, we are packing significantly more trains onto the exact same physical network, totally avoiding the astronomical costs of laying down new steel lines. It is a true masterpiece of engineering efficiency.
That brings us to the end of our deep dive. I hope this structured breakdown has really illuminated the incredible logic keeping us safe at 300 kilometers an hour. As we push closer and closer toward fully autonomous trains, it leaves us with one big provocative question. Just how much further can we compress the physical space between us before the physics themselves break down? Thanks, we can see you in the next video.